On behalf of the Perelman School of Medicine and Penn AI Tech, I'm honored to welcome our distinguished speaker and recipient of the Dean's Distinguished Visiting Professorship, Dr. Mayur Naik, from Penn School of Engineering and Applied Science. The Dean's Distinguished Visiting Professorship Program, featuring faculty nominated by their deans, recognizes stars on the Penn faculty to promote collaboration with School of Medicine researchers, and we're thrilled to have Dr. Naik here with us today. He earned his PhD in computer science from Stanford, worked as a research scientist at Intel Labs before joining Georgia Tech as an assistant professor. He joined the Penn faculty in 2016 and now serves as a full professor and graduate group chair in the Department of Computer and Information Science. His research focuses on programming languages and machine learning with an emphasis on general purpose neuro-symbolic approaches that combine deep learning and logical reasoning. His research is motivated by the need to make AI applications more interpretable, data efficient, safe, and easy to develop. The goal of the Dean's Distinguished Visiting Professorship is to engage our community in excellent science done locally and to nucleate ideas for collaboration. As you listen to this talk, I'd encourage you to think about possible opportunities for interactions. Welcome.
Thank you very much. Thank you very much for this kind invitation. It's my great pleasure and honor to be here with you today, both those here physically, but also those who are online. This talk is going to be about challenges and opportunities. And what I mean by that is I'm going to talk about challenges that are faced by the users of large language models in medicine as well as in other fields. And the opportunities are what my research is aiming to do to address these challenges. And the way I'm going to bridge this gap in my talk is by first telling you about what the current practice is for using LLMs. And in this process, I'm going to tell you about what its limitations are. And then I will have set the stage for telling you how my research is addressing these challenges. So here's the outline of my talk. I'm going to first introduce what large language models are. And then the bulk of my talk is going to focus on three key challenges that LLM users face and what the solutions are in the current practice and in my own research to address those challenges, namely hallucinations, specialization, and alignment. And finally, I'll conclude with key takeaways. Okay. So let's begin with a gentle introduction to large language models. You might be curious where these models are being used today. It all began with the software engineering industry. That was perhaps the first and most popular use case of large language models in the real world. This survey, which was conducted by GitHub, which is the largest platform for software development, both open source and proprietary, showed that even a year ago, that 92% of programmers were already using AI tools. So it isn't the future, but it's the present. And they reported, for example, being able to program 55% faster using AI tools. Another key domain that has witnessed a dramatic use in AI tools is law. In fact, AI has come after law repeatedly, but this time it seems to finally be gaining traction. There's a wonderful article in the New York Times which says how lawyers are essentially, if anything, word machines, and so this seems to be a particularly attractive application area for AI. And last but not least, it is happening in medicine as well. So here's, for example, an article about how Microsoft has integrated its AI models with Epic EHR systems for doing everything from routine administrative tasks, such as transcribing clinician voice to text, but even summarizing entire patient histories during a patient visit from EHR data and so on, right? So you might wonder, what is a large language model, right? The simplest explanation I can give is that it's a neural network which predicts the next word in a sequence. So what you see here is a neural network. And if this network is especially large, then we call it a large language model. And it can take an input like the one you see here. The cat likes to sleep in the, and it essentially produces a probability distribution over possible next words, right? And as you might imagine here, the word box turns out to have the highest probability. And indeed, it would be a sensible thing for this neural network to output. Now, how are these neural networks trained? Well, we have an abundant amount of text on the internet today. And so we don't need expensive labeling of data by human experts to train these models. And this paradigm is called self-supervised learning. So the supervision or the labels to train these enormous models is coming sort of without any human intervention. And the way these models are trained, for example, let's revisit the sentence we had earlier. The cat likes to sleep in the box. Even this simple sentence provides a lot of opportunities for this model to train itself on predicting the next word. For example, after the word the, there's some probability that we are talking about a cat. And as this sequence gets longer and longer, the model is incentivized to predict the word that you see shaded over here, which is called the masked word, right? And so merely by this simple exercise of learning to predict the next word in a sentence, we can have enormously powerful models that we see today, like ChatGPT. Turns out that you don't have to train these models just on short sentences. You can train them on entire paragraphs or passages, okay, such as those on Wikipedia. And what we have learned a few years ago is that if you can even train these models on computer programs, on the source code of these programs. And these programs ultimately are text. And they even have interspersed comments in natural language that further help these neural models to gain interesting knowledge. Now, this was what I called what's called pre-training, right? Once you have trained a model, you can now iteratively do next token prediction. So for example, in this case, if I give it the sentence, a trained language model can, the highest probability token would presumably be generate. And now subject to that new sentence, a trained language model can generate. The next word that is most likely could be coherent, and so on and so forth, right? So just by doing next token or next word prediction, we now see these models being able to generate entire passages of text, right? But this was only part of the training of these models. And we actually call this pre-training, right? It is, in this case, this model is trained on enormous amounts of data from the internet, books, and videos, and so on. But the problem is that we end up with a model that can essentially babble on about anything, but is not aligned to what we might want it to do, such as question answering. So there are typically two additional phases of training. The second stage is what is called instruction fine-tuning. In this case, we teach the model to respond to instructions. And unlike in pre-training, where there was no supervision from human experts, now we actually have humans write a bunch of question answer instructions in the form that we'd like this model to respond. And then there is an optional third step called RLHF, reinforcement learning from human feedback, Just because a model has now learned to respond to instructions, it might still not have what we call human values. So we'd like the model to actually produce output that is closer to what humans like. And once again, we have human experts um, take different outputs that this model is producing, in this case, about writing a haiku about paper clips, and rate these responses. And with these new labels, we can further align the model to what uh, outputs humans like the most. Okay. We end up having a plethora of large language models this way. There's no one size fits all. In fact, many of the models you see here were released literally in the last month or two. Many of you will be familiar with OpenAI's GPT-4 or Anthropic's Claude 3. But there are other models, for example, by Meta, there's Llama 2, Gemini by Google, and there's a French company which produced a new model called Mistral, and most recently, Databricks produced a model called DBRX. So you might wonder, what is different about these models, right? There are four essential differentiators. The first is, what were these models pre-trained on? And to give you a sense of the scale of the amount of data, these easily can range into what are called trillions of tokens, right? And this is just for GPT-3, which came out years ago. The size of these models is another key differentiator. And today, GPT-4, for example, is estimated to be over 1 trillion parameters, okay? And here the size of GPT-3 is just 175 billion parameters. Two other differentiators are the context size. So how big can the prompt be? And while it was just around 2,000 words for GPT-3, with Google Gemini Pro, it's already 1 million tokens, right? So you can have enormous pieces of text or even entire PDF documents given as input to these models. And finally, even the architecture of these models, of these neural networks, is evolving. The most popular is what is called the transformer model. But just the last few months ago, we have what is called Mamba, and then mixture of experts and a hybrid of transformer and Mamba, so-called Jamba, and so on and so forth, right? So because of this, we have a lot of different LLMs to choose from. Let me pause here and see if anyone has a quick question about LLMs before I proceed to the challenges.
Can you just explain the idea of architecture more?
Yes. So architecture it defines how the neurons in these neural networks are interconnected. And this architecture has gone through several evolutions over decades, and transformer is the most sort of the one which led to this enormous breakthrough. It would take me an entire hour to explain the transformer architecture, but essentially it turns out to be sort of a specific way to connect these neurons that gives each word what is called attention to all the other words in the sentence. So the next word that is produced by the model uh, takes into account the influence of every other word earlier in the context. Okay, so let me now talk about the challenges and opportunities that I mentioned at the beginning of my talk, starting with hallucinations. So I'm going to talk about what are hallucinations, why they occur, what is the current practice to avoid them, and why it doesn't work as well, and finally, what we are doing to reduce them. So put simply, hallucinations are just a phenomenon where a model generates output that humans would think is incorrect or nonsensical or not real. And here's a surprising recent example. Even these enormous models that we have today fail at doing simple reasoning like the form you see here. Is a kilo of feathers heavier than a pound of steel? Right? And the answer obviously is yes. and GPT-4 does get it right, but other models which are equally good or better in other respects get it wrong. And there are many other such examples. They fail at plain arithmetic, at common sense reasoning, at reasoning about multimodal data, right? Which is, for example, image and text combined and so on. And so one can imagine that if they cannot even answer something as simple as this, how are they going to reason about much more complex medical data, right? Now, why does this happen, right? Why is it a fundamental limitation of LLMs? I'm going to give a very simple analogy here. Um, in the data set, we can expect, for example, these 4 sentences that you see at the top. And when a model is trained to just do next word prediction, then at test time or inference time, if I give the prompt I, then it is most likely to pick the completion love iPhone repeatedly, because that is what it saw most frequently in its training data set, right? Here's another example. If I give the prompt as the word he, you can see highlighted in this data set, there's one instance of the word he, and so the model would have been incentivized at training time to complete it with the words would and like. But then when it gets to the word to, it might, for example, interpolate between these 2 instances of to that it saw in the training data and do what is called crosstalk to complete it with something and a similar thing happening again with the word the, to ultimately yield a sentence which we would think is nonsensical, right? So this seems to be a fundamental problem, and no matter how big a model you might build or how much training data you might use, it fundamentally seems to have this problem of hallucinations, right? So I'm going to talk about a few different ways in which you can reduce it today and leading to the work we are doing, which helps give even better assurances. And as I'm going to go over these techniques, there's going to be an increasing amount of effort that will be needed from the data scientist who is applying these techniques. So let's start with something called prompt engineering that some of you might be familiar with. It's the easiest technique in a data scientist's toolbox when using a large language model. So what we learned early on, in fact, in the year 2020, was that you could give a large language model a few examples of questions and answers and ask it to complete the answer to the final question. Now, any human, for example, could see the first 2 examples here that I've shown in the prompt. But and turns out that, for example, for the question Barack Obama, we might expect the output to be K and A. And as you might guess, we are expecting the LLM to take the last letter in the first name, followed by the last letter of the last name, right? That's the pattern you see in the first 2 examples with Elon Musk and Bill Gates. But incredibly, I tested this with GPT-4, the latest model from OpenAI, and it couldn't get it. And for example, with Barack Obama, it produced the output AM, right? And so you might think that, if large language models cannot even do something as simple as this, do we have hope for other kinds of reasoning, right? Turns out that in just a couple of years, in 2022, there was this remarkable insight that in hindsight is not surprising at all, that because it is doing next token prediction, if you give more information in your prompt, for example, with just one example, in this case of Elon Musk, explaining why you expected the output NK, okay, this is called chain of thought prompting. Turns out that the large language model immediately gets it and does give the right answer, in this case for Barack Obama, along with an explanation of why it is producing that answer, right? Later on, there were results which showed that even without giving the reasoning in the prompt, you could simply ask the model to think step by step, and it picks up on a lot of internet examples where there is literally the sentence, let's do this step by step, and it gives the correct answer. This was shown to work not just for the kinds of tasks I was showing you so far, but for everything from strategic question answering to sports understanding to robot instructions and so on. And what you see here is these models are starting to even outperform humans, which you see by this dotted line, especially as they get larger and larger. This is sometimes called emergent phenomena, that as the models get bigger and bigger, you've seen the number of parameters in the billions, in this case, up to 540 billion parameter models, their accuracy on these tasks grows dramatically. So higher is better, right? And so much so that even previous architectures, which was supervised by humans, are now falling behind, which you see by this dotted line. Okay. You might ask, is there a single prompt that works for all tasks? Because as you might imagine in medicine, we might want, for example, to ask the model about many different tasks without having to go through the trouble of giving the chain of thought for each task, right? And so, as you might imagine, you might want to make a single giant prompt for different tasks and then use it for all tasks, including unseen ones. And turns out that there was this remarkable insight just last year, which showed that if the bigger the prompt gets, the models start forgetting what was there in the prompt. So here's a nice illustration which shows that the models only tend to remember what was there in the beginning of the prompt and what was there at the end of the prompt, but they forget what was there in the middle of the prompt. And so this leads me to the next technique you might want to use, which is to essentially fine-tune the model. Whereas prompting just steers the model to a different completion, fine-tuning actually changes the weights of the model, as I'll show you shortly. But let me give you an example of how good prompting can be, especially with an extremely large model like GPT-4. This is a wonderful paper which came out last year from Microsoft, which showed that by combining various prompting tricks that I showed today, you can get a chatbot built on GPT-4 that actually does remarkably well on various medical question answering challenges. Okay, so not just for example, for college biology, but also for many other domains like medical genetics, anatomy, and so on. Right? And what you see here is as you use each of these techniques, such as few shot prompting, which I showed, and augmented with chain of thought, and even, for example, use what is called an ensemble approach, which is shuffle these examples that you give and then take a majority vote. All of these end up with a dramatic accuracy of up to 90.2, right? Merely by prompting. Okay. Now, as I said, prompts, as they get more and more unwieldy, it becomes especially challenging for the model to remember everything that was said in its input. And so there's this other technique called retrieval augmented generation, which also has another benefit besides just being able to support extremely large prompts, which is that LLMs are trained on a certain date, and that is called its knowledge cutoff. And so now if you have some data that was not there when the model was trained, you simply cannot afford to retrain the model on these updates. This is even true for big tech companies with enormous resources. And so there's a technique called RAG, or retrieval augmented generation, which allows you to augment a pre-trained LLM with what is called an information retrieval system. Let's look at an example. So in this case, let us say I have these 5 documents. Think of them as articles on Wikipedia. I could store all of these documents into a database, which is called a vector database, as opposed to a traditional, say, relational database that you might be familiar with. And now comes along a question: which board game was published most recently, Pirates Cove or Catan? In this case, what we can do before invoking an LLM is we can ask which of these documents in the database are most similar or have the information that is most likely sufficient to answer this question. And in this case, you can see easily that words such as pirate scope occur in certain documents, and so does the word Katon. But the word Katon occurs in many other documents, but they're not selected because we also want to know something about the year in which these documents were published. And now we can go to the next step, which is to build a prompt which has only the sufficient information that was extracted from the database. And now a large language model is able to give the correct answer, which is pirate score. If you don't use retrieval augmented generation, what I'm going to show you here is, again, what GPT-4 does. If you simply put all the articles, in this case, about 8 of them, which are just the first couple of paragraphs from 8 Wikipedia articles, even a large model like GPT-4 goes off the rails and gives the wrong answer, right? So now you might think, does retrieval augmented generation solve all the hallucination problems we are seeing? And the answer is no, that at scale, even this technique starts failing because there are various pieces in this architecture that you're seeing here, which is how are we so-called embedding the question and the documents, how are we chunking things, and finally, how we are generating the response to a given question. So this remains an area of active research, and it is far from perfect. Okay, great. And as I said, this, while it is has lesser hallucinations than pure prompting, but it is by no means guaranteed to be free of hallucinations, right? So that leads me to the next technique, which is fine-tuning, right? So unlike prompting, fine-tuning actually changes the model under the hood to give you better domain or task-specific performance. I'd like to note here that the model doesn't gain any new knowledge as such. You are simply realigning it to a certain style, as I'll show you with an example shortly. And here's an informal cartoon, which shows you the different techniques that I've been talking about. Early on, you might want to start with prompting and gradually move on to retrieval augmented generation. But ultimately, if you want high task performance for your specific tasks, you might want to do fine tuning. And if you start with a bigger model, then you'll end up with even higher accuracy than if you started with a smaller model, right? Here's a nice example from OpenAI, which collaborated with a startup, an early startup that applied LLMs to a case law in the United States called Harvey AI. Essentially, they took 10 billion tokens worth of new data to fine-tune this model, starting with case law from Delaware and then expanding to all the rest of the United States. And incredibly, in a user study with attorneys from the top 10 large law firms in the United States, it was found that this new custom model that was obtained, these attorneys preferred their output more than the vanilla GPT-4 97% of the time. And the main reason they cited was reduced hallucinations. Okay. So this shows you the power, and here's a nice illustration. If you did not fine-tune the model and used it for case law, GPT-4 gives pretty bland output, whereas this custom trained model actually is much better suited to talking about this particular domain. Okay. And this is also essentially what Microsoft is doing with Epic EHR. It is certainly using prompting and retrieval augmented generation, but it has also fine-tuned these enormous models to Epic's needs. Okay. Let me now take you to the final part of this toolbox for reducing hallucinations, and this goes into my own group's research. So there's this belief that that human thought occurs in two modes, which are called System 1 and System 2 by noted psychologist and Nobel laureate Daniel Kahneman, who passed away just last month. And he has this book called Thinking Fast and Slow, And one can view large language models as essentially a glorified system one. And no matter how much you tweak the prompts or do fine tuning, you ultimately just have a better system one. So system one can be thought of as the mode of thinking, which is more instinctive. For example, when you add 2 and 2, you don't actually follow an algorithm. You instinctively know that the answer is 4. But if I give you a question such as what is 17 times 24, then you wouldn't instinctively fill in the response, but you would actually follow a decision process that is more logical before arriving at the final answer. And so what LLMs are lacking is this system two, right? And so my research is about integrating the best of both worlds, deep learning and classical algorithms, which is this field of computer science that predates deep learning. And I've listed the pros of both of these systems. For example, system one is great at rapid reasoning, handling noise and ambiguity, learning from the context and so on. But system two is great at, for example, using domain knowledge, which would be, for example, very helpful in the field of medicine, right? And doing complex reasoning, giving explanations to its output and so on, and generalizing better. And this paradigm has been come to uh, be known as neuro-symbolic AI. We have our own solution that is based on this paradigm called Scallop. So it's a new programming language and tool chain for building neuro-symbolic applications in various domains. And it supports symbolic reasoning over rules that you can write over essentially tabular data, over relations. And it turns out that you can model different kinds of data using relations, right? Including different kinds of EHR data. Furthermore, Scallop also integrates with a wide range of neural models, including these large language models like GPT, Llama, and so on. I'm going to show you some simple examples here using Scallop. What you notice here is an input table called mountain. In this case, let us say we do not want GPT to hallucinate on the names of mountains. So we want to provide them through a spreadsheet or a table. In this case, you see 4 mountain names: Everest, Fuji, K2, and so on. And now we want as output the height of each mountain. Now, this is something that probably GPT has learned from Wikipedia articles. And so we might have more trust in GPT filling, say, the heights of mountains, but not their names, right? And with just one simple, a couple of lines of code in our language, you can essentially invoke GPT on each row of the input to fill in the corresponding row, the height of the mountain in the output. You might wonder, does this only work for textual data? And the answer is no. It also works for multimodal data like images and video and audio and so on. I have a simple example here where we use OpenAI's CLIP model, which connects language with images to essentially classify or label images in the input given a list or a set of labels. In this case, CLIP correctly identifies the first image as that of a dog with probability 0.99, and for the first image here as a cat with probability 0.98. Okay. And once you know whether the image is a cat or a dog, you can go on to do further processing in our language with it. You might wonder, are there only these simple examples that I can write? And the answer is no. We can write very complex applications here. This would again be very relevant to something like medical applications on top of EHR data. So here we have a task called visual question answering with common sense reasoning. So you're given an image here of these 2 giraffes, and you're asked, you're given a question in natural language to identify the tall animal on the left. And it's easy to see that the answer is a giraffe. But in order to build an application, an AI application that can give you this answer reliably, you might want to go through a lot of domain knowledge uh, expressed in the form of traditional relations that you see in Excel or Oracle DB or MongoDB and so on. Right here, what you see is a knowledge graph, which, for example, tells us that giraffe is an animal. And this helps the AI understand that when we are talking about a tall animal, that it is okay for giraffe to be the answer, because we know from the knowledge base that a giraffe is an animal. Okay. Okay, so here are some metrics that folks in medicine would be especially interested in, and they go beyond just accuracy. So the first, what you see on the left is generalizability. Can we, for example, train this neuro-symbolic model on easy questions, but get it to reliably answer harder questions, which have longer and longer chains of reasoning in the knowledge base? Okay, going from chains of length 2 all the way to chains of length 6, labeled C2 through C6. And we see across the board that with Scallop, it can actually generalize better on harder questions. Okay, so higher bars mean better in terms of accuracy. But it's not just in terms of better generalizability. We also know that medical data, clean medical data, is hard to come to curate, and so Scallop, by virtue of using a knowledge base, can also give you better accuracy with lesser data, right? So for example, in this case, even with just 10 samples of the training data, it gets better accuracy than existing approaches. But as you give more and more training data, obviously the model gets even more accurate. Now, here's the future of Scallop. So we continue to build it. There are a lot of challenges that we are solving for this paradigm to be widely usable, the way deep learning is. We have recently integrated it with the favorite programming language of data scientists, which is Python, and existing popular machine learning frameworks like PyTorch. But we are all happen to be at a university where we ourselves have a lot of interesting use cases. And I've just begun working with a few professors in our medical school, notably the oncologist Ravi Parikh, and folks from DBEI, Chi Long and Li Shen, on various problems in clinical decision support, drug discovery, and so on. And in all of these problems, there is a real need for neuro-symbolic integration. You can learn more about Scallop by either reading our papers and tutorials or trying it out yourself. I'm going to now switch gears to the next topic, which is specialization. And I have a lot less to say about specialization and alignment than I had to say about hallucinations. And I'm going to go a bit faster in the interest of time. So if you recall from the case study that I showed you with Harvey AI, it made sense to specialize a large language model to your own needs, right? But I'm going to show you why it is hard and what the current practice is to mitigate this problem and what we are doing to address it, right? So here's the typical workflow. If you want to specialize a model, let us say you are a data scientist in the medical school, you are going to go and get one of the pre-trained models from this website called Hugging Face. And then you're going to collect a bunch of in-domain data, label it, and now fine-tune this model, evaluate its performance, and repeat the cycle if the performance is not good enough. Okay, you might go and collect more data, you might change the base model that you got from Hugging Face, and so on. And ultimately, you'll get a model that you are happy with. Okay. Now, there are multiple challenges here. The first being, how do I even curate the data? right, for fine-tuning. And this is especially a problem that is severe in the medical domain, where you have a lot of missing or biased data in EHR. There's also the challenge of what model to begin with. This is a website which compares different models using ELO ratings, which you might have heard of in chess, in professional chess. And the same way we can use humans to rate the outputs of pairs of models, right? And so far, what we see is models like Claude 3 and GPT-4 are doing much better than other models. But it's not just a single model that is good for all use cases. Here's a nice survey that the venture capital firm A16Z conducted recently, where they are seeing enterprises using multiple models in production. And there are various reasons for this. They don't want to get locked in to a certain model provider, or they want to quickly take advantage of the most recent model and so on, right? Let us say somehow you solve these two challenges, right? That you collected sufficient clean data for your fine tuning, and you also know which model to fine tune. There's still the question of how do you go about specializing it, right? And remember that these models are becoming bigger and bigger, right? What you see on the left is a log scale. It is the amount of compute you need in terms of petaflop days to train some of these models. For example, GPT-3, which is already a fairly outdated model, needed 4,000 petaflop days to train, right? So for, say, a data scientist who has a single server at their disposal, right? In this case, an NVIDIA machine with, say, 4 RTX cards, 2080 cards with 48 GB RAM. It's pretty standard to own such a server. The best model that you can even begin fine-tuning is something that is already fairly outdated, right? You might wonder, can I take an outdated model that is small and fits on your machine and somehow get great performance out of it? And the answer is no. If you look at the task of protein folding, AlphaFold, which came out 3 years ago from DeepMind, had just 21 million parameters. You can easily fine-tune that today on even a laptop, but it wouldn't be as good as starting out with ESM2, which was released by Meta. So it's an open source model for protein folding that came out more than a year ago, but it has 15 billion parameters. And so you couldn't even begin to fine tune this model. And you can read about how much better ESM2 is even compared to ESM1 across a wide range of metrics for protein models, right? So this becomes an accessibility issue. So what can you do if you have, for example, up to $1 million? That is what you would need to purchase a system to fine-tune a state-of-the-art large language model today. But clearly, this is out of the means of most data scientists out there, right? So then you can say, well, I'm going to use cloud compute from maybe one of the big 3 providers, Microsoft, Google, or Amazon. But you will be surprised at how expensive this can get quickly. Here's the cost by a Reddit user who says that just deploying a model based on GPT 3.5 for 20 days cost them $3,500, right? So what do you do now is it's a very manual and labor intensive process to figure out exactly what base model might fit in the memory that you have, and what is the best quality that you can get at the fastest speed that is possible. And the reason there's a trade-off here is you would ideally like to have as large a model as possible, because that is how you're going to get better quality, but that is going to affect both the memory and the speed, right? So there's a tension here between how good a final model you want and how large a model you can start with. And there's a cookbook of optimizations here tricks that you can use to somehow fit these models. And I'm not going to go into the details of these in the interest of time, but essentially there's a rapidly expanding array of these optimizations at your disposal. I already talked about various prompt layer techniques, such as few shot and chain of thought, but there are many at the weight layer, okay, such as quantization and RLHF and so on, but even further lower down at the hardware level. And new ones are constantly coming up every month. So what my research is trying to do is, instead of the current practice where a data scientist might spend many days and a lot of money on compute, uh, and keep repeating this process until they get a model that fits in memory, has acceptable quality, and runs fast enough, to getting this and maybe an even better model, but automatically and efficiently, right? This is a project that has just begun 6 months ago, so we are not ready to share much information yet, but we are planning to open source it this summer, and I'll be more than happy to work with different folks in Penn Medicine to help you with your fine-tuning needs. Okay. I can show you quickly some initial results that we got just this week. So what you see here is a bunch of undergrads and a first-year PhD student have finally managed to put together a portfolio of these optimizations and show that, in this case, the metric I have is what is called perplexity. It's a well-known metric in large language models on something called wiki texts. So we are fine-tuning a model on Wikipedia articles of interest. And higher perplexity is worse, so lower is better. And obviously, as you shrink the model more and more using these optimizations, the model's quality gets worse and worse, which is what you see here, right? And so you want the smallest model with, what I mean by that is the most bits, percentage of bits removed, that gives you the lowest perplexity. And you already see some very interesting examples here, solutions here, which have fairly low perplexity. In fact, as good as the perplexity of the model, which was which was not shrunk at all using these optimizations, right? And so we aim to automate all of this search that you would have to do manually otherwise. Okay, so now I'm going to go to the very last part of my talk, and I'm almost done here. So I told you about neuro-symbolic programming, and I told you about specializing large language models. I didn't yet talk about higher level desirable properties like safety and ethics and empathy. Again, properties which are especially important for chatbots and domains like medicine, right? This is work in progress, not just my own research group, but even the big tech companies don't quite understand this yet, as some of you might have seen by the recent fiasco that Google had with its release of Gemini. When you specialize models with the objective of accuracy, it has been shown that actually you end up degrading the guardrails that the original model had, such as safety and other benefits. So you see a wide range of these desirable qualities that we might want in a model that were essentially broken the moment you specialized it to your needs, right? And this is something so new that it hasn't even yet been presented at this conference called International Conference on Learning Representations. It'll happen later this year. In the domain of medicine, here's a nice study which shows that on the left, you have the pre-trained models such as Llama and GPT, and on the right, you have fine-tuned models to the medical domain. And across the board, you see that these fine-tuned models violate even the AMA's principles of medical ethics, right? So what you ended up trying to do, which is tailor these models to the needs of clinicians, end up actually breaking the properties that they desire. Now, there are two ways to fix this. You can either hire a lot of experts to label the outputs and rate them, which is prohibitively expensive, using a process called RLHF that I described early on in my talk. But what is emerging is a new approach, which is to use these large language models themselves as judges, right? And so you can automate this whole process. And in fact, it has been shown that LLMs as judges achieve more than 80% agreement with human experts on whether a piece of output is ethical or safe or toxic and so on. And so this actually fits really nicely with slim scale, where the user has to just essentially give qualitative alignment metrics, such as toxicity and safety and so on. But that we can convert to quantitative ones, such as scores, using LLMs as judges, right? So with that, I'd like to conclude my talk. What I started out was giving you an introduction to large language models. And anyone rarely, if ever, will use these models off the shelf for their use cases, right? And I call these a vanilla system one. They'll keep getting bigger and better, but they will never approach something that you can achieve by specializing and aligning them to your needs. Okay? And even that would only give you a better system one. The ultimate trustworthy AI model that you could hope to build, would be one that combines system one and system two, using this emerging AI paradigm called neuro-symbolic programming that we are working on. So thank you all for your attention, and I'll be happy to take any questions.
Do you want to do the questions from the Q&A from the online folks first?
Sure. Yes, so the first question is, does UPenn hospitals use any Gen AI in clinical/administrative applications now, or in plan in the near future? I wouldn't be the right person to answer this because I have very limited exposure to what UPenn hospitals are doing. My best guess would be that everyone is experimenting with this technology. People are especially averse to using them in patient-facing scenarios because of all of these problems that I currently discussed. Okay, but things are rapidly changing, so I won't be surprised if these would find their way in use sometime in the near future, especially through a provider like Epic, which is already deploying it. Okay, so the next question is, how would you suggest a small size provider to start using Gen AI? How big a data science team needs to be? What should be the structure, timeline, and performance expectations? So I think one should follow the cookbook of techniques, which I showed you, starting with something as simple as prompt engineering and proceeding to increasingly expensive techniques, right? It doesn't make sense to start with something as expensive as fine-tuning first. And hopefully the cookbook of techniques I walked you through could be a good starting point, right? So always start small, but then gradually use more resources where necessary. Okay, the next question is, does Scallop use a graph database? Which LLMs do you start to train? Do you use Penn Hospital EMR to train? And what do you see? Do you see that it can be used in clinical practice? So Scallop is still, I would say, a research tool. This is the summer will be the first time where we expect to have much broader usage. It doesn't use a graph database. It actually uses a relational database. That's the paradigm which has withstood the test of time, as you see with Oracle DB and Microsoft SQL Server and Postgres and so on. Typically, the LLM that we start with is something like GPT 3.5, but because it is closed source, we also use Llama frequently, right? I don't have much experience with Penn EMR data, but we are starting to actually experiment with Flatiron data for oncology. So very limited experience there. Do you see using AMD inference chips is better for edge computing? So this is a great question. So NVIDIA, while it is best for server side computing, for edge computing, I believe Qualcomm is the best at this point, but there'll be many emerging hardware vendors in the near future, including, of course, AMD. Okay. But definitely I would look at Qualcomm's chips for edge computing. So there's another question, which is, many hospitals are using Gen AI for medical documentation. Yes, so for many of these in-house use cases, that is where I expect Gen AI to have the initial impact in healthcare. Sure. There's a follow-up here regarding the hospital LLM use case. Lots of exploration into how we can use this both to improve workflow as well as to improve care delivery. So this is a comment rather than a question for those interested. And finally, what ethical considerations arise with the use of language models in medicine, especially regarding decision-making processes? How do you think these concerns should be addressed by the Congress? So we are in the very early days of regulations, both in the United States and in the EU, right? I believe the consensus is that one should not prematurely regulate these systems. Even as I said, alignment is the thing that is least well understood right now. We don't even have a great hold on things like hallucinations, which are more objective. Alignment is something far more subjective, but we have seen incredible progress, as you see in these couple of papers that I cited here, okay, with using LLMs as judges. Thank you very much.